Okay, so welcome back to our second part of our exam review with the midterm exam. In the previous lecture, so last time, we went over more or less just like proving things and giving like logical arguments for why something may be true. We might touch on that a little bit today, but mainly I wanted to focus on the other types of problems that will appear on the exam. So, for example, let's say problem. Maybe I would ask you to say translate. This quantification, I suppose. Into English. Okay, so we want to translate this into English. And I'm only going to put one up here, but this is probably the type of problem where it would be like 4 of them. Like problem 2, part A, part B, part C, part D, and they're each like this. Just like translate A through D. Okay, so these typically most students will get because we kind of have learned to use this type of language since we introduced logic, right? Like that's how we talk now, right? And it's important to remember that even though like it might like be easy to remember, like when you first showed up to this course, like you would have no idea what that is. So that is the universal quantifier, and we know how to say that, right? So we can just say for all. And then we have a domain of interest right here. And that's an element sign, right? So X is a element of the reals. So there's a bunch of different ways you can write this. I would say maybe like for all real numbers X, maybe. And then the square of X is never equal to -1. Maybe you could say something like that. And that's it. Right, so I'm hoping that this is like a almost like a freebie type of question. Okay. Now this is a rather simple one, maybe. Like there's only one quantifier, right? So you might want to be concerned about maybe another one. Like I'll do one more. Like I'll just put this like part B. I'm not writing all that over again. So for all, I'm not going to say it out loud. So when y'all can do it with me. How complicated are these? So now there's 2, and then maybe like I'll also ask like translate it and give me the truth value. I could easily see that as a question. Like translate it, and then the truth value would be for this true. Right? And then here, translate this, and then give me the truth value of it. So the solution here. And let me make sure that this is being picked up. Okay. This would be let's say for all real numbers x, and then we have the existential quantifier right there, right? There exists a real number y, and then maybe such that. And then the truth value of this is true. Or is it true? Is it false? What is the truth value of that statement? How's it going? So it's false, right? If x is equal to 0, there is no y that will multiply x to make it equal to 1. Right? So, and this is the universal quantifier, which means it has to be true for every possible real number x. So you see how that could trip you up. It's like, think carefully about like the extreme cases. Right? All right, so I think that is good enough for those. So it'll be like 4 of them underneath one question, probably worth like 5 points each. And that'll be it for that. Before I move on to the other types of problems, I do want to say that you need to be able to determine like this. Like, which one of those is true or false? That's the empty set, by the way. Correct. So this is false, and then this is true. Okay, because that is not an element of that set. Okay. However, in my one of my YouTube recordings, I show that the empty set is a subset of every set. Okay. You all remember that proof of why that is a subset of every set? How about we just like I like give that proof again, just because it's important to remember is like what does it mean for it to be a subset, right? Everything in this set is contained in that set. So let me just actually, because I didn't give that in the live lecture, let me just like reemphasize that. Theorem. So let's say so if A is a set, then the empty set is a subset of A. That's the thing that I proved in one of the recordings. Okay? So we need to recall like the definition of being a subset, right? So like, again, just the definition. Like B is a subset of A is equivalent to, it's like if and only if, that's like logical equivalence basically. So if and only if for all x, if x is in B, then x is in A. So if this is a tautology, then that's true, right? This being a tautology means that B is a subset of A. So for all x, if x is in B, then it better be in A. right? That's the definition of a subset. That tautology. Or not tautology, like if it's true, then that's the case. So it has to hold for every single x, right? So here the proof is actually like very simple. So maybe they notice that for all x, if x is an element of the empty set, then x is element of A. Like this is logically equivalent to, well, for all x. What's the truth value of that? The hypothesis of that conditional. It's false, right? The empty set is a set with nothing in it, right? Okay, so I just replaced that proposition by what it was. It's false. Okay. False implies anything is always true, right? False hypothesis and a conditional is always a true statement, right? The conditional is only false when the hypothesis is true and the conclusion is false. Every other time it's going to be true. So this is true. So that, which is the definition of being a subset, is true. So it's just like, hence, the empty set is a subset of A. This is what's called vaccuously true. When the hypothesis of this conditional is false. Always. Like that's always false, so it's just vaccuously true. There's nothing to really check. Yeah. So that's why it's important to remember the empty set is a subset of every set, but not necessarily an element of the set. Okay. Sometimes the empty set can be an element, right? Like, for example, like that's true, right? One of the elements is the empty set. Okay. But what about this? Is that one true? So this one is good. That's true. Okay. It's false. It's false because the empty set is not an element in there, right? What is this element? How would you call this element here? Yeah, the set whose element is the empty set. So like that's false, right? The empty set doesn't appear in there, but this set containing the empty set does. So like that's not in there. So like that would be false, but if you did this, that's true, right? And then for all of those, the empty set is a subset of each of those. Doesn't matter because it's a subset of every set. Right? Like A can be any set you want. The empty set is always a subset. So you know that for a fact. The only time it gets tricky is when there's like sets containing the empty set, and you have to be careful about what the symbols mean. Okay. Let's see what else. More that we'd like to pick like a few computational type of things. Okay. So let's say let A be the set 1, 2, 3, 4, 5. and B be the set 0, 3, 6. Find the following. Part A. Say like A union B. Part B. A intersect B. Part C. A set difference B, and then part D, B set difference A. So you're like just calculating these properties. I mean, calculating these sets based off of those operations. So, what are they? Right? Thanks. The solution right, A union B. That's the set with elements. So what is the definition of a union? Right? The union is the or. So it's like X such that X is in A or X in B. Like that. So if you can satisfy that logical statement, then you belong in that set. So what, like this is the disjunction, right? So if that's true, then the whole thing's true, right? It doesn't matter, like if at least one of those is true, then it's true, right? Which means that like everything, like from all of them are going in there, right? Like, does 0 belong in there? Well, is 0 there or there? Yeah, so that would be true, the whole thing's true, it goes in that set. And then the same thing for all the other ones. And there's no repetition because it's a set. B, A intersect B. That's a set of all X such that X is in A and X is in B. Like that. So now this is the conjunction between that proposition and that proposition, right? So the conjunction is only true when they're both true, right? So like, would 0 go in here? No. Because that'd be false and that'd be true, but together it's all false. Okay. So you only want things that are in both of them. So it looks like 3. Right. So then move to the set differences. So A set difference B, that's equal to the set of all X such that X is in A and X is not in B. Okay, so would 1 go in that set? So 1 is in A, okay, and 1 is not in B. So 1 would go in there. What about 2? 2 is in there and 2 is not in there, so we're good again. What about 3? 3 is in there, and that's false now. Right? So then 3 wouldn't go in there. And then you just keep this process going and you see what it does. In part D, B set difference A. That's the set of all x such that x is in B and x is not in A. Okay. So that'd be 0 and 6, right? Yeah. Also, I like giving problems that ask you like to make conclusions about things. So for example, like yeah, I would like look at like problems like 27 through 32. So 27 through 32 in the Rosen PDF from this set operation section. There's like those are all like fair game.
For these, do you want both answers, like the set numbers and the like set domain?
I wrote that to remind you of the definition. That was it. Maybe. So then also I do like problems involving multiple unions and multiple intersections. So for example, like this type of problem. So let's maybe, let's see, let me pick a good one. I don't want to say. So like, like let's AI equal I infinity. So that's like that interval notation on R. I would ask you to maybe find the union from I is equal 1 to infinity of AI and the intersection from I is equal 1 to infinity of AI. It looks more difficult than it is. You just have to think about it and understand the notation. Right, so just recall, and I'll even put this as like a hint, or like I'll put this on the exam. Like recall that the union from I is equal 1 to infinity of AI is equal to A1 union A2 union A3 union ... up forever. And then the intersection is just equal to all the AIs intersect each other. And I like these types of problems because it's like discussion of them in class is very, if barely existent, if existent at all. And it would like kind of test how well you interpret notation and ideas and what's going on here, right? So it's like kind of pushing you to take time to think, which you'll have because you'll have several hours to complete it. More than enough time to complete it, the exam. But like, okay, in order to understand this, we need to like understand what the A's are first, right? And that tells us, so if we put whatever I is there, put an I there, right? So maybe like, I'm gonna write more than what's necessary, but just to be clear, like A1 is equal to the half open interval 1 to infinity, like that. That's from like college algebra or something. It's just that interval, right? A2 is equal to 2 infinity. Dot, dot, dot. That's how, like, that's what they are, right? They're just intervals. And what this is asking you is to union all of them and then also intersect all of them and see what you get. So it might help, to draw something. So here's the real number line. 0, 1, 2, 3, dot, 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 right? So what does A1 look like if you're going to shade it in, just like you're in a college algebra course?
A1 will be like here, simple.
And then all of those numbers there, right? And it's closed, right? Closed there and it just goes off forever. Okay? That's A1. And we want to maybe union that with what's A2. Well, A2 would be like, so all of that, right? So isn't it the case that A2 is a subset of A1? Yeah.
One, we, oh, never mind.
Yeah, so the way that we make them is just whatever index there goes there, right? So A2 is a subset of A1, right? What about A3? Where's A3? Take all those numbers there, right? So what's going to happen when we union all of those numbers? Like that's because that's what this is asking. Like, what's the union? Yep, that's it. And the picture kind of tells us that. Like all of these other sets are contained in that one. So whenever you union them, you're just going to have the biggest one. Yeah. So union I is equal 1 to infinity. The I, in this case, is equal to this one. That's it. And drawing the real number line with that picture will help with that kind of problem. Now, looking at it, again, like here's A1, here's A2, here's A3. Like just so what do you think the intersection of all this is? Well, maybe focus on like
Two, three.
so on that note, so what's A1 intersect A2? A1 intersect A2.
Two.
It's A2, right? It's 2 to infinity, right? So what's A2 intersect A3? Well, you can just say A3, or you can say 3 to infinity. Okay? What's A3 intersect A4? So what do you think the intersection is? But then that intersect AI plus 2 would be AI plus 2. It is the empty set. Why do you think that's true? Like, and maybe there'll be like a bonus thing, like explain why it's the empty set. Y'all have proof techniques. You wouldn't have to prove it, but maybe I'll give you the opportunity to prove something like that if you encounter such a question. So let's just play with it. So by way of contradiction, it's messy because I'm running out of room, but by way of contradiction, suppose that the intersection from 1 to infinity of AI is not equal to the empty set. I just suppose that it's not, and you, like, if this is correct, you should find a problem that occurs immediately. Maybe not, I don't know. So if it's not equal to the empty set, that means that it contains at least one element, right? It has at least one element in the intersection. So then, like, okay, then there exists some, I guess I'll use like the lowercase x. It's an element of this. Right? If it's not empty, then it has at least one element, right? We'd assume that it's not empty. Right? But what does that mean? It means that x is an element of A1, right? It means that x is an element of A2, right? If it's in the intersection of all of them, it has to belong to all of them, right? Right, the intersection, the only things that make, like, in order for something to be in this, it better be in that, and that, and that, and that, and that forever, right? So maybe x is an element of AI for all I equals to 1, 2 to infinity. No, you don't write the infinity symbol like that. You just do that. Okay. This should be some type of, there should be a problem here, right? Maybe we can find it, maybe we can't. But my first thought, like if we're going to try to reason about it, is just to assume that there's something in there and then there must be like a problem somewhere, right? So what could the problem possibly be? It's in A1, it's in A2, it's in A3, it's in A4. It's in, well, they do, right? Like, it can't be in there. Like, because that, if it's there, then it's not there, right? If it's there, then it's not there. If it's there, then it's not there. If it's there, then it's not there. If it's there, then it's not there, right? So like, it's almost like it's always being pushed. Right? So maybe, again, this is not something I would ask you to do in the exam, but like maybe that's an idea. Like it's that x is somehow being pushed. Think about that. You see what I'm saying? Like if you assume x is in here, that's false. Like it wouldn't be in the intersection because it has to be over here to be in both of these. But if it's in here, then that's also false. It needs to be over here. So what's happening to the value of x? it's being pushed bigger and bigger, but X is a number, right?
It's actually,
Yeah,
it's X a real?
yeah, X is a real number. And maybe I should have wrote that. Some real number X, so it's like, and again, this is like a really, really messy argument here. I'm just trying to give you the idea, right? There's some real X in there, right? X is just a number, right? It's just a number. But we just observed that if it's going to be in there, it's always being pushed bigger and bigger and bigger. So that's where I see the problem, right? So, like, I don't know. What could we do? Do we have any like for or ceiling or nearest integer functions that we might be able to use? For example, like in the functions section of Rosen and also in the Xi book, you learned about these like floor and ceiling functions, right?
We keep the flow function of AI.
So what we could do is say something like this, right? So like, what does the floor function do? It's like the
It makes the decimal become.
an integer, right? An integer, right? So like if X were like some like 3.5, right? The ceiling you could go, it would make it would be 4, right? So what we can do is we can say something like this if we want to be clever. Let n equal the ceiling of X, right? That's valid, right? N is just a ceiling of X. It's the nearest integer to X above it, right? So then X could not be an element of a n. And I'll just write out what that is. Oh, actually it could be, right? It could be if X was equal to n, right? Like if X was an integer. So we have to be careful about that. We can fix it by doing this. +1. Right? So then, like, n is definitely bigger than X, right? N is definitely bigger than X. So X cannot be an element of n because n is bigger than X, right? A contradiction. What's the contradiction? The contradiction is that, like, somewhere down the line here, here is an, right? And then X is like definitely at least 1 away from it, right? So X cannot be in that one. But to be in the intersection, right, it has to be in every single one of them, right? X is in AI for all integers, I mean, all natural numbers I. How can it be in all of them, but not that one? So there's like a little bit of cleverness that we had to do that incorporated using the ceiling function. X could be any real number, like so any positive real number. So we use the ceiling function to make sure that we get an integer bigger than it, greater than or equal to it. And then we add 1 to make sure that it's like definitely X is less than that n. And since that's an integer, it's in that sequence of sets. So it was just like a trick. Not a trick, it was a technique, an idea, right? And the idea stemmed from what? Noticing that X was always getting pushed. Like if we assumed it was in there, it wouldn't work. So it had to be in here, right? And if it's in there, it had to be in there. So X was always getting bigger and bigger. So, right, like that was the catalyst to this thing, right? So we suppose by contradiction that's not empty. Then there exists some real number X that's in the intersection. If it's in the intersection, it's in every single one of the A's, all of them. Okay, So what we do is we make a new number that's an integer and definitely bigger than x. And then x cannot be in that A, because this is the interval from n to infinity, and x is at least one less than n. That's a contradiction, because it has to belong to all of them, but it doesn't belong to that one. Does the logic now make sense? Like the idea. Again, I wouldn't ask you to do it, but you might have a chance to like try to prove something like that. I would just want like that. But again, like the hesitation when this was first claimed, the hesitation was like, it was almost like it was a guess, right? Like your intuition was saying like, okay, how could like just, but what was behind what saying that? It was because we see that it's always moving somehow. So to capture that, I assumed by contradiction and got that, and then the rest is already explained. Okay. All right, so on that note, I will ask questions about the floor and ceiling. And these actually, in the slide book, I'm sure there are plenty of examples of floor and ceiling. Right? As computer science majors and data science majors, knowing how to convert like floating point approximations to like nearest integers and up and down fashions is important to know in many algorithmic aspects. Because algorithms iterate by integers, and if you have like reals, you sometimes need to convert those to integers, and that is important. Okay, and the sequences are functions from the natural numbers to real numbers. That's definitely been covered. And then discussing like cardinalities of sets, like if I give you sets, find the cardinality, how many elements are in the thing, right? I'm not going to ask you to prove anything with cardinalities really, but you should be aware that like you need to know how to count the number of things, right? Like you're just aware of like general like properties. So like if A is infinite and B is a finite set, then their union is infinite. Their intersection would be finite. It's either empty or it has the things in B only. Right? So important things. And yeah, I think that's going to do it. So I'm going to go ahead and stop the recording now. It's a little bit earlier than I thought, but